Linear types allow us to do safe memory management without a garbage collector. We give each piece of data a unique owner so that the ownership graph is a rooted tree. We can even get memory leak freedom if the type system ensures that every data structure is eventually deallocated. For message passing concurrency, linear types can also guarantee deadlock freedom. Ownership is not unique in this setting because the channel between two threads is owned by both. But we do get deadlock freedom because the communication topology between threads is acyclic. The topology can change dynamically, for example, if we send channels as messages. Such reasoning about changing graphs and linear ownership makes mechanized proofs difficult. This paper is about a technique for encapsulating this reasoning in a generic framework. We provide a connectivity graph abstraction with a separation logic for reasoning about linear ownership of edges. We demonstrate this framework by giving a mechanized deadlock freedom proof for a session-typed language. Here is a picture of a connectivity graph. The graph is an abstract representation of the program state. The red boxes represent threads and the blue circles represent channels, and edges between them represent references labeled with their type. Channels can also reference other channels if they are stored in the buffer. Each vertex in the graph has a separation logic predicate that asserts ownership of edges. This predicate links the graph structure to the physical heap and thread pool. We maintain the invariant that there are no cycles in the graph, even if we are allowed to traverse edges in both directions. This means that the graph is an undirected forest if we forget about the direction of the edges. Such an invariant allows us to do proofs of deadlock and leak freedom in the style of progress and preservation. To prove deadlock freedom, we have to find a thread in the graph that can make progress. We do this by annotating the edges with red waiting triangles. These indicate which side is waiting for the other side to perform the next action. We can then find a thread that can make progress by starting at any vertex and following the edges in the waiting direction. Because the graph is acyclic, we always end up at a vertex that is not waiting for anyone else. We formalize this search with an induction principle that we call waiting induction. It is parameterized by a binary relation R that indicates the waiting direction relative to the edge direction. The induction principle intuitively says that to prove a property P of a vertex V, we may assume that P already holds for all the vertices that V is waiting for. In order to make use of waiting induction, we need to maintain a well-typed and acyclic connectivity graph. This involves constructing a new connectivity graph when the program steps, and proving that the types on the edges correctly describe the new heap and thread pool. We provide a set of separation logic lemmas to apply local transformations to the graph. These lemmas ask the user to prove a local separation logic entailment. The proof of that entailment determines how ownership of edges is transferred between vertices and how the types on the edges are updated. The lemmas don't care about the language semantics because they are parametric in the local invariant that holds at each vertex. We have mechanized all results in COG. The main body is a generic connectivity graph library that is parameterized over the vertex and label sets, and also over a local separation logic predicate for each vertex. The library then provides a generic invariant construction that says that there exists a connectivity graph such that the local predicates hold for all vertices. It then gives separation logic graph transformation lemmas that can be used to prove that the invariant is preserved as the program executes. It also provides the waiting induction lemma for proving that deadlock and leak freedom follow from the invariant. We apply this to a session-type lambda calculus with both unrestricted and linear types. It has concurrency with asynchronous channels and recursive types, including recursive session types. We then used our framework to prove deadlock and leak freedom for this language. To our knowledge, this is the first mechanized proof for such a language with dynamically changing communication topology. We first tried to prove this using a monolithic approach, but we did not succeed because the proof goal became too complicated. But after we had our generic framework, the language-specific part of the proof was relatively small and straightforward.